Good day, everybody. This is Nithiya, working as assistant professor in CSE department in Kalangar Institute of Technology. Today, I am going to lecture you about paging and structuring of a page table. Before entering into the topic of paging, I'd like to explain you why we jump into the concept of paging. So first, we get the process. I mean, if you have any process which is of more than 2 GB or something which is of larger memory, what you really do is you need to load the entire process into the main memory for your execution. In order to do that, we go in for a concept of swapping. So swapping requires you swap your entire program into your main memory, apart from noticing of your memory allocation and how much memory your process is going to be occupied. Apart from these constraints, you're going to load your entire program into your main memory. So in order to do that, you're getting some of the wastage programs, that is the programs that is occupying the main memory, not using it, but it just occupies the main memory space for a longer time. Those type of processes are chosen and it is brought back into the secondary storage. So that way your main memory has larger space to occupy your larger process. This is the basic methodology. So whereby we come across various disadvantages. These disadvantages are overcome in the paging concept. In this paging concept, what we really do is we go in for a contiguous memory allocation system in swapping. That is, when you want to project your process into your main memory, you need to fit that exact size into the main memory. So what you do is you swap out the wastage process and swap in the necessary one. So what paging does here is, it is not going to see about the memory which is in sequence manner. The memory space need not be in sequence manner. Rather, what it does is it segments the pages, it segments the process into various types of pages. Those pages can be loaded into the main memory at any location. So this helps the main memory not to allocate extra process or not to give any extra spaces for unnecessary memory units. So here we call frames, that is main memory. Your physical memory is divided into frames and your logical memory is broken down into pages. Your logical memory is the process that you are going to load into your main memory, and the frames is the main memory segments. So the pages are loaded into available memory frame from the backing store. Backing store is your secondary storage devices, just a storage unit you use to load your needed pages into your frame location. For doing all these process, we get into two criteria. One is the page number and the page offset. Your every process carries this page number along with page offset. Page number, as its synonym indicates, page number is something that you have in your book. You have your page numbers which tells about which page your content is present and so on. That concept is followed in page number. And coming to page offset is your displacement path, at which page number inside your process your current page is located. That is your page offset. So the value of page number along with page offset is combined in your process. So this gives the page table structure. So next one is, when you deal with small amount of process, it's well and good. You can go with your page table and load your pages. Appropriate pages gets mapped to the main memory and search for a frame, and it gets executed in a smoother way. But in case of a 64-bit logical address, when you go beyond your 32-bit logical address, it is going to occupy a more number of page tables where you need more number of frames to load your entire pages. So I'll tell you with an example. Suppose if you have pages of more than 100 programs. If you have 100 programs and 100 programs have 100 pages, and suppose if you consider P1 to P100 is your program and P1 consists of 10 pages. Each page should at least carry of 4 KB, 4 KB of memory space, then imagine how much you need to occupy those 100 processes into the one single memory location. Yes, it needs million entries, but this is not a good idea. This is not going to work out in an efficient manner. So to handle this drawback, we have 3 methodologies. One is hierarchical page table, hash page table, and the third one is inverted page table. We'll look one by one in the lectures. Hierarchical page table, as the name hierarchical indicates, it is the flow from the smallest to the biggest or the biggest to the smallest. Anyway, we indicate a flow model. We are dividing the page table into 2 segments. I'll explain you with the diagram. This is the outer page table and this is the inner page table. Hierarchical paging model, we are dividing the page table into 2 levels. The outer page table contains the index part of the inner page table. We usually tell that page table carries the segments of pages, but over here the page table carries, yes, the segments of pages along with the process. Suppose consider it is P1, P2 and P3. P1 consists of segments of pages 1 to 500. P2 consists of segments of pages 100 to 700. P3 consists of segments of pages 921 to 900. Sorry, 900 to 929. So P1, P2, P3 has an index part that should be mapped to the outer page table. Something that you call your book index. So that book index consists of chapters, and those chapters consists of some contents where a page number is mapped. The same logic is applicable here. You have an outer page table where you have an index part that leads to an arrow mark to the page table. Each page is mapped to the main memory frames. This is a 2-level paging system that is followed in hierarchical page table. As we have seen in the diagram, P1 is the outer page table index, P2 is the displacement within the page table, and D is at which level or at which position your searched page is located. So next one is your hashed page table. Hashing function. We have heard hashing in so many places. Hashing refers to some value need to be encoded and some value need to be decoded. When the sender sends any information to the receiver, he just adds some hashing function to his original message. Thereby the receiver decodes that hashing function to retrieve the data. The same process is followed over hashed page tables too. But the difference is we are not going to deal something about hashed functions. We just use the concept of hashing. So this name is termed as hashed page tables. If the logical address is same, if we have more than 32-bit logical address, we go for these 3 methodologies, and the second one is hashed page tables. Here the hash value is the virtual page number. Virtual page number is similar to that of the logical addresses. This logical address will be generated by CPU. So hash value is the virtual page number in logical address. Here each entry in the hash table, it contains a linked list. So earlier we have paging table. Each process consists of set of pages that is loaded in the page table. Here these process consists of pages that is represented in a linked list format. Linked list format you have learned in data structures, where it defines about 3 fields. The first one is your virtual page number. The second one is the value of the mapped frame, that is your main memory frame. And the third one is the pointer to the next element, whereby we will be searching the entire linked list to find out a particular page in that particular process. So algorithm that is used is virtual address is hashed into the hash table. I'll explain you the diagram and then we'll get back to this algorithm. So first one is your logical address generation, where you have process P that is given to the hash function. You are searching for this particular page. So in the hash table you are searching for the page under the process P1, which is in a linked list format. First you are searching for page P. No, it is not present. Yes, over here it is present. So corresponding frame number is retrieved and the displacement value is taken over here. So in this frame, under this displacement, your page P is present. This is what it is explained in algorithm. Virtual address is hashed into the hash table. The virtual page number is compared with field 1. Yes, we have compared and then we got the resultant value. So the next one is your inverted page table. Inverted page table is something we retrieve the real page frame of the memory, whereby the virtual address of the page stored in the real memory location with information about the process that owns the current page. Suppose if you consider over here, the CPU generates the logical address, which is the process P1, and the corresponding page of the process P1 and the displacement. It is searched in the search table. Thereby we found that at the index ith part we get the information about the real page that should be loaded into the physical memory. It tells about something called real page. The real page is brought from the main memory because the real page, whenever we retrieve any real page, that indicates that process could not avoid this page by switching into any program or something. So suppose if you consider your case statements, every other case statement should be executed, but the index part, the declaration part cannot be avoided. That is chosen as a real frame. When memory reference occurs, the part of the virtual address that consists of your process ID, process P1, along with the page number. P1 process carries 5 page numbers. Your page number 3 is your real page number. That information is presented over here. The inverted page table is then searched for a match. Now the inverted page table searches for a match. It gets the match and then it returns the physical address. If there is no match, then it displays as illegal address has been attempted. So if you get any match, then it will be looked up in the looked up table and it should be arranged in a according order. So that's all for this lecture. I hope you have gained something. I'll just give a quick feedback. Now, in this we have seen about paging and how we are structuring your page table by hierarchical manner, hashed based manner, and your inverted page table. In hierarchical, we go in for outer page table and inner page table, and in your hash based value, we something used for as a hash function, and we retrieve our physical memory location. In inverted page numbers, what we do is it is exactly different from those of the two. In inverted page number, we get the real page that is loaded in the main memory, and we search in for the page table where the exact references is made. So that's all for today's lecture. I hope you enjoyed it, gained some knowledge, and thank you. We'll see you in the next lecture.